Okay, I'd like to go over some homework problems that was material that we covered in our last lab session that we didn't really get a chance to review as thoroughly as most of the earlier. So I'm going to start out with uh, the beginning of homework uh, assignment 2b. And in that one, got the wrong one here. That one, we examined the empirical rule, incorrectly spelled here, by the way. Hopefully you can correct that. In the empirical rule, we had mentioned that there are certain assumptions that we can make about a normal distribution. Let's sketch that out. Unfortunately, I don't have uh, my graphics tablet, so it's going to be a little harder for me to do this, but I'm going to see if I can't use my trackpad to at least get us a decent look at what these things might look like. Okay, so we know that in the empirical formula, matter of fact, I have a version of this that I can use to start out with. Let's see if I can come up here. Here we go. Okay, so we have a version of this that we can start out with, and we can see that within one standard deviation of the mean of a typical standard normal distribution, we have about 68% of the population. And within 95% of two standard deviations of the mean in either direction, we have 95% of the population. And outside of that, we have about 2.5% on one side, 2.5% on the other side, because we know that this normal distribution is also symmetrical. There's a lot of things a lot of extra information that we can get from this empirical formula, or the 68%, 95%, 97% rule. For instance, we know that between the mean and one standard deviation below the mean, we have about 34%, half of that 68%. And above two standard deviations of the mean, we have what remains between 50% and 34%, or 16%. And about 13.6% of it is in here, and about 2.5% of it, about 13.5% is in here, and 2.5% is outside of two standard deviations above the mean. And same thing on the other side, below the mean. Okay, so a lot of things that we can deduce from this. So we're going to apply that to some problems. Okay, let me open up one that we actually worked on for the homework, or that you guys seem to be having at least a decent amount of success with on the homework. Okay, let's see. Okay, so population known to be 160, could be anything. Standard deviation is equal to 60. So, what's the probability that a single observation selected at random from this population would have a value less than 100? So the mean is 160, the standard deviation is 30. So if I go back here, what does that tell us? That tells us that the mean is 160. Kind of hard for me to do here. And the standard deviation is 30. Sigma is equal to 30. Okay, well, let's see. 130 would be one standard deviation below the mean, and the mean would be 160. So to answer that question, what's the probability a single observation selected at random would have a value of less than 130? Well, it would have to be the area to the left of the 130 or below one standard deviation. So if this is 34%, this whole area is 68, and this is 34%, that leaves 16% below one standard deviation below the mean, or in other words, below 130 in the case of this particular standard normal distribution. Okay, so the standard normal distribution really has a specific meaning. It refers to the normal distribution if the mean were 0 and the standard deviation were equal to 1. And that's the distribution that the z-table is derived from. So I really shouldn't call it quite that. But we'll just call it a good normal distribution. Okay, so let's take a look at the second part of this problem. Okay, what's the probability that one individual from this population has a value higher than 190? Okay, well, 190 would be 30 above 160, or in other words, one standard deviation above the mean. So the probability that they would have a value higher than 190 if we selected someone at random. It's going to be the same that we had down here. The 34% and 16% of this distribution is above that. So that would be about 16%. Okay, remember, this empirical is really an estimate more than anything else. And we'll get into more precise measurements shortly. Okay, so now that we know, if I had asked what's the probability that we would randomly select an individual whose value, whatever this measurement is below 190, only 16% of the population has a value above 190, so that leaves 84%, the rest of this area, below 190. So that's the way we would make that deduction to answer that alternative to this question. Okay, so if this were 190 and this were 16%, then the area below here would be 84%. Let me talk a moment about how I'm using the areas here. These areas underneath this distribution can represent two things. They can represent the entire population, the distribution of these values, whether they're weights, blood pressures, or whatever, for the entire population. Or you can also look at it as the probability that you would select a random individual within this population. The probability that, for instance, that their weight, let's say it's weight, that their weight would be 100, below 160. Well, we can see that that's the mean. So probability would select that person would be 50%. Probability above that would be 50%. And again, as we said, probability of 190 or above would be 16%. So we look at it both ways: distribution of the population, or the probabilities that we would represent, that we would select someone at random from the population who would have that value. Okay, so let's take a look at the next version of this question. Same population. What's the probability of selecting one individual from this population who has a value between 130 and 190? Well, between 130 and 190, we have 68% of the population. So that's the probability we would select an individual within that range. Okay, what's the probability that we would select an individual less than 130 or greater than 190? Well, both the lower tail here and the upper tail satisfy that. So that could be 16%. Plus 16% with a 32% chance of selecting someone in one of those two ranges. Let's take a look at the next part of this. What's the probability of selecting one individual that has a value less than 130 or greater than 190? We just answered that question. Same population, with the probability an individual has a value less than 100 or greater than, let's see if I can't read that, less than 100 or greater than 220. So let's take a look. Let's go back here. Less than 100. Two standard deviations with 100. We two standard deviations below the mean. And 200, what was that again? Let's see, 220, I believe. There's going to be two standard deviations above the mean. I think that's what that said there. Okay, yep. Okay, so what's the probability of selecting someone that would be below 100 or above 100 at 220? One standard, negative two standard deviation, or positive two standard deviations. Use the negative and the positive to indicate whether we're to the left of the mean or to the right of the mean. Okay, so the probability that you would be within two standard deviations of the mean is going to be 95%, right? So the probability you would be outside of it, below it, or above it, and since this is 5%, 5% of the distribution is left. And in fact, we can also say that this would be 2.5%, and below two standard deviations or below 100, and this above would be 2.5% also, because again, normal distribution can be expected to be symmetrical. So those two tails are going to be equivalent. Okay, so I'm going to move on to another question where we're going to look at, do the same kind of analysis, except that it's going to involve the use of a more precise measurement. One way to do this is to actually have a table that helps us calculate the areas under this distribution. And another way is to use a function in Excel to accomplish that as well. So we're going to take a look at that now. Here, let me get this away. Let me clean this up so it's available to us again. Oops. Okay, good. And I'll close this. And we'll open this. Okay, let's take a look at this. The amount of money spent on books by Hunter students in the semester is normally distributed. This is important. We have to know that our distribution is normally distributed because a lot of our answers are based on assumptions that go along with normal distribution. Okay, mean is 249 and the standard deviation is 30. For our purposes, on the homework you'll do the exact calculation. For our purposes, I'm going to call that 250. Okay, so what's the probability that a randomly chosen student from this population will have spent more than $300? Now, a lot of you can probably get away without sketching this, but I like to sketch it because I know it'll help me avoid making errors. So if the mean is 250, remember I rounded that to simplify things for our calculations. And the standard deviation, is equal to 30. Okay, let's take a look at where that value, what was that value we're looking for again? Let's see if I can. What's the probability a chosen student will have spent more than $300? Let's take a look at where that's going to be. So that's going to be, let's see, 30 and $200, $300 is 50 over 250. So it's going to be, it looks like it's going to be over here somewhere. 100. Right? How do I know that? I know that because one standard deviation above the mean is going to be 250 plus 30 or 280. Oops. Up. Or 280. Okay. And two standard deviations above the mean is going to be 60 added on to 250. So it's going to be more than 300. It's going to be being closer to 310. Okay? So I can kind of see where I'm going with this. The probability that we're going to select a student that's going to be above 300.
It's 3 o'clock.
It's going to be somewhere around. It's going to be somewhere around. I would say maybe about. Let's see, maybe about 8% or something like that. But we're going to take a closer look and see how we can accomplish this. Okay, we can't really use the empirical rule because we're kind of guessing at this stage. So instead of doing that, we're going to go to another tool that we have, which is the z-table. In order to get a z-table, z represents the number of standard deviations. So in this case, how many standard deviations above the mean are we? Well, we can use the general formula. The difference between the value we're interested in and the mean divided by the standard deviation is going to be the number of standard deviations. So z is going to be equal to, in this case, 300 minus, 300 minus 250 over 30. That's 50 over 30, so this is going to be equal to roughly 1.67. I'll round it to the third decimal, at the second decimal place. So it's going to be roughly 1.67 standard deviations above the mean. So we're going to want to determine what area, what percentage of the population of Hunter students is going to be above that. So now we have a very interesting tool to do that. Let's take a look at that tool. Okay, that tool is this normal distribution. So I can't get to that a little easier. Actually, I'm going to open that up another way. Okay, here we go. So these represent all the z-scores. Notice as we go to the left of the mean, the z-scores are increasingly negative. And then we come to 0, which is the mean itself. And as we get away from the mean, the z-scores become increasingly positive. This table gives us a summary of the areas under the mean to the left of the value that we're choosing for that z-score. So anytime we look up a z-score in here, the number that's in the center here is going to represent the area to the left of that value. So as you would expect, the value of z-score 0, which is the mean, you would have half the distribution to the left of that. Okay, so we're going to look up our value, which is 1.67. So in our case, it's to the right of the mean. You can see this shaded area is to the right of the mean because this table has all the positive z-scores. This table has both negative z-scores and positive z-scores. When you're working with other tables than this, keep an eye on the description of what these areas represent, because some of them may give you the area between the mean and the z-score value that you're looking for. Some of them may only give you positive values for the z-score, so you have to use your knowledge of the fact that the normal distribution is symmetrical to figure out the areas. But so there may be some curves on that. So for our purposes, for the exam, maybe it's best, and for the homework, but currently, that we stick with the z-table and get familiar with it. So we're going to look at 1.67. So a z-score of 1.6, and this is 1.7, so it's between the two. In order to find the third decimal, we're going to go across on these columns. Each column is going to represent the last place, the second decimal place in our z-score. So it's going to be 1.60, 1, 2, 3, 4, 5, 6, 7. So it looks like 0.9525 is the area that's going to be to the left of our z-score. So this is going to be the area going that direction. It's going to be 0.9525. And this can show you my estimate was pretty far off here. So that's why we're not using the empirical formula. And what is that going to leave? That's going to leave the difference above there. Or it looks like 6.75%, or stated as probability, 0.0675. Okay, so probability of randomly selecting a person that has a Hunter student who has spent more than $1,000 on their books is about 6.75%. Probability of selecting a Hunter student who spent less than $300 on the books is 93.25% or 0.9325. Right? So we can use the z-table and our understanding of normal distribution to solve a problem like this. Let's take a look at it from another perspective. Let's see, the amount of money, but what's the probability a randomly chosen student spent between $200 and $300? Okay, so how might we solve that problem? Well, $200 is going to be roughly the same amount below here, right? So it's going to have, let's see, z is equal to 200 minus 250 over the standard deviation of 30. So it's going to be minus 1.67, right? So minus 1.67. What's the probability they will have spent less than that? Well, in fact, we kind of saw the converse of that, didn't we? Now let's look up minus 1.67. Minus 1.60, 1, 2, 3, 4, 5, 6, 7. That represents 4.75. Oh, I made a mistake. We'll go back and correct that. That 4.75%. That's 4, 0, 4, 7, 5. Right? And on the top here, and let's correct this right now. This was 0.475, and that was 93. Was that 93 or 95? I bet you that was 95. That's probably where I got that wrong, right? Okay, sometimes you learn a little bit more by getting it wrong. Yeah, see, I transposed that correctly. It's 0.9525. My math was right. My reading was incorrect. Okay, so that was 95.25%, and that leaves 4.75%, 0.0475 above value, and it leaves 0.0475 below this value. So if the question were, what's the probability of selecting a student who spent less than $200 or more than $300, it would be the sum of 4.75% and 4.75%, or 0.095, like 9.5%, 0.095. If the question is, what's the probability of, let me just write that down, 0.095, which is the probability of selecting someone that's in these tails, right? 4.75 each, 0.045, 0.0475 each. When I add those two together, the probability of choosing someone from either one of those tails is going to be twice that. I add it together, it's going to be 9.5%. If the question were what the percentage of students, and this is actually the question was, what's the percentage of students that then between $200 and $300? Well, it's going to be 1 minus that, because the whole is 1. It's going to be 1 minus that, so it's going to be 90.5%, right? 90.5%, or as a probability, 0.9050. Hopefully I got that right without making any further errors, and I'm sure I'll hear from you if I did get that wrong. Hopefully I got it right, though. But I'm pretty sure that by looking at this, you'll get the idea of how we can manipulate the information that we have, or utilize the information that we have in this table, and the fact of the normal distribution being symmetrical, to figure out what these areas per population, how these populations are distributed, and what the probability is of getting different values when we sample someone randomly from this population. Yes, let's go back. We can take a look at the next problem. Next problem, let's see what we wound up there. Next problem, we moved over to interpreting binomial distributions. Okay, so I'm going to say save. Get rid of that. Okay, and I'm going to open up this here. Okay, so let's see. Just before we go any further, I want to point out to you that I can use Excel instead of the Z table to give me a value for an area in that distribution. For instance, I can say there's a value called norm. That's this. That stands for distribution. And if I put parentheses in there, it prompts me for the z-score. So if I put in a value for the z-score, such as minus 167, and hit enter, it gives me the same value that we got from our table, 0.0475, which is the same value that we got before. Now, conversely, I could use a value called norm S inverse. And now it asks me for the probability. I put the probability in here, or the z-score in here, like that, or the area under the curve in there, they'll give me the opposite. In other words, the z-score that value represents, that area represents. Work out the same way for positive values, the z-score as well. And again, this is always going to give you the area. The norm inverse, norm S disk will always give you the area left of the z-score that you have asked for. Again, if I put norm S disk, parentheses, I put positive 1.67 in here just fine, I'll get a much larger value, because it's going to be the whole area to the left of this value, which is our across on the right. And it's going to be our 95.25%. Okay, actually, I think, did I get 95.5? All right, you got to forgive me. It's I'm a little jet lagged. The values may be a little off here, as you say. So things are I'm a little bit sloppy here with my math, but I'm sure you get the idea on this stuff. Okay, so I'm going to go on to binomial distribution. Actually, I'll leave this open. Of course, we're going to do something interesting here as well. Let's open up a problem involving the binomial distribution. Okay, I believe that this one will do. Let's take a look at this problem. Study indicates that 4% of American teenagers have tattoos. You randomly sample 30 teenagers. What's the likelihood that that sample will come back with exactly three teenagers that have tattoos? Let's take a look at this. Now we know that the probability in this population of, if you randomly select one teenager, probability is 4% that they're going to have a tattoo. If we wanted to know what's the probability if I selected two teenagers and they both had tattoos, we know that would be the multiplication would be 0.04 times 0.04. Just like flipping a coin, 1/2 times 1/2. What's the probability of all three of them if you selected three having tattoos? 0.04 times 0.04 times 0.04. Well, now we're faced with what's the probability of having three teenagers out of 30 that you've selected that have tattoos? Well, now it's a problem because now we have many different possibilities. You could have the first teenager could have no tattoo. Second teenager might have a tattoo. The second, fifth, and ninth might have tattoos. Many more might have tattoos. Many fewer may have tattoos. So many different possibilities. To calculate them all, you would have to do a number of calculations involving factorials and combinations. You may have seen that formula. You may recall that formula from the lecture. Okay, so we have a lot more possibilities to deal with. So we need to use a function called the binomial distribution. And you may remember that that can distribute itself almost normally in a lot of cases. But we're going to get to that in just a little while. Let's see if we have the function in here that we can use in Excel to do this calculation. So I'm going to type in equals and binom dist and put in parentheses. And this binomial distribution function, it asks us for four things. First thing is number S, or number of successes. That would be how many meet the criteria we're interested in. In other words, the three students that we want to know have tattoos out of 30, how often that'll occur exactly. Okay, the number of trials is the number of students that we sample, which in our case is 30. And the probability of any individual student having a tattoo, 4%, 0.04. And I'm going to say the next thing I'm going to put in there is false. And we're going to come for cumulative. We're going to come to that in a second. Decide why I'm doing that. I'm close these. Hit enter. And the probability that if we select 30 students at random, probability that exactly 3 out of the 30 will have tattoos is about 8.5%, 8.6%. So let's take that again. Let's try that again for 2. 2, comma, now 2 successes, same number of trials, same probability, and false, and hit enter, and that's the probability for 2, a lot more likely, right? Because likely outcome would be 4% of 30 would be about 1 or 2 students. What about for 1? Okay, 4, and false, get comma, false, again. Okay, there it is. That's quite a bit more likely. And now, of course, possibility we might have 0 or none. Let's include that. 0, no teenagers having tattoos. Don't seem too unlikely, does it? 0, 30, 0.04, comma, false. Okay, and if I were to do this for every possibility, this is 0, this is 1, this is 2, this is 3, this is 4, and we could have 5 and 6 and 7 and 8. If I were to do this for every possibility, I'd get down to 30, right? Okay, the sum of all the probabilities is going to be equal to, of course, 1. Okay, every possible outcome would add up to, when I add them all up together, probably for each of every possible outcome would add up to 1, as we would expect. Now, most likely values are going to be down at this end because the prevalence of these is low. So I would expect it to be a very rare event to get, say, 25 out of 30 having tattoos if it's really a random sample. Well, now let's take a look at that false and true. One of the things I may notice that if I looked at What's the probability of having three or four tattoos? One way for me to calculate that would just be to add up all of these possibilities for three or fewer. 3, 2, 1, or 0. It comes out to about almost 97%. Well, let's see what happens if I had used binom dist, parentheses, and if I had said to myself, 3 successes, 30 trials, probability is 0.04, and what if I say true here for cumulative? Well, in fact, what that does is it gives you the same value as adding up that instance, 3, and all the values below it. So it's cumulative all the way back to 0. Okay, so that works out that way. Well, now you could ask yourself, what's the probability of getting more than 3? Well, getting more than 3, probability of getting more than 3 is going to be 1 minus the probability of getting 3 or fewer. Well, what's the probability? This can get a little tricky, though. What's the probability of getting 3 or more? Well, 3 or more would include all 3 and above. So what I would want to do here, calculate the probability of getting 2, and subtracting that from 1. So 1, oops, equals 1 minus, oops, no, actually, no, I got, it has to be cumulative. Okay, and 2, comma, 30, comma, 0.04, comma, and true. So this value would give me the probability of 2 or fewer subtracted from 1 would give me the probability of 3 or more. And that would be 11%, would be 3. Okay? So a lot of ways to look at that, but you have to be a little bit careful about the wording of the problem to decide how you're going to apply this binomial distribution calculation to the particular problem that you get asked. Okay? Again, from what I've seen in the homework that have been completed, you guys have been picking up on this because most of you got this right on the first draft. Now, there is one other consideration that we might have. Okay, that is, take a look at this idea. You may recall that a while ago we were looking at the a Galton machine, a machine in which, so I have somewhere I can draw here, a machine in which we had balls drop down and they would hit pins, right, that were distributed in such a way that each ball that came down had a 50-50 chance each time of going left or right. So you have a different number of left turns and right turns. So it's very improbable that a ball would go left all the time, right? If it's really 50% chance. Much more probable that it would be somewhere towards the middle. We saw when the balls accumulated, they appear to distribute themselves in normal distribution. Most of the values towards the center, fewer and fewer occur on the outskirts, on the outside, further and further away from me, makes it less probable. Okay, so now that normal distribution is based on a binomial occurrence. This left or right turn is a 1 or 2. So we can kind of represent this binomial distribution as if it were a normal distribution. I mean, in other words, we could say, let's approximate the values that we would get by doing the specific calculations by assuming for a moment, in some cases, that we can describe this as a normal distribution. Okay, so next problem is going to take a look at that. Let's take a look at this problem. And in this problem, 40% of Hell's Angels have tattoos with mom on them. Okay, what's the probability? What would be the mean number of Hell's Angels with mom tattoos for repeated samples of size 50? Okay, so in other words, if I repeatedly took samples of size 50, right, n equals 50, right? Well, if 40% of Hell's Angels have mom tattoos, right? In other words, the probability equal to 0.4, 0.40, okay, then the most likely outcome is going to be 20 out of the 50 will have tattoos. That's 40% of 50. Okay, so I can represent The mean outcome, if I did this over again, the average outcome that I would get for the number of bikers with mom tattoos, the mean is going to be equal to 20. How did I get that? I got that by multiplying the sample size times the probability. Okay, that's simple. U is equal to the sample size times the probability. Now 50. Well, if we're going to approximate a normal distribution, the next thing we're going to know is the standard deviation. And in this case, without too much of an explanation, the standard deviation is going to be equal to the sample size times the probability of a successful outcome, in other words, they have that tattoo, times the probability of the opposite, 1 minus the probability of having that tattoo, in other words, not having that tattoo. So standard deviation in this case is going to be equal to the square root of 50 times 0.4 times 0.6. Okay, so let's give that a try. Let's get the calculator out. Okay, so let's see. It's going to be 50 times 0.4 times 6. And that's equal to 12. That seems like an improbable standard deviation for this distribution. We've forgotten to take square root though, right? So square root. Okay, there we go. And that's going to be equal to 2.3, it looks like. Yeah, rounded off for our purposes to 2.3. So now we have a standard deviation, and we have a mean, so now we can predict what these outcomes might be. So what would be the mean? Mean we decided was the 20. The standard deviation for the distribution of repeated samples of size 50 is going to be 2.3. Using the normal approximation normal approximation of binomial distribution of this binomial distribution, and the z-table, what's the probability that a random sample of 50 Hells Angels would produce more than 25 bikers? Okay, so what's our z-score going to be here? Okay, here's our distribution, 20, right? And standard deviation is equal to 2.3. Okay, so it means 20. So what's our z-score? Okay, we're looking at 25. Probability that we would have more than 25 bikers that have that tattoo. We'll see it's going to be equal to the value we're interested in, 25, minus the mean, which is 20, over 2.3. Okay, so that's going to be 5 over 2.3. Okay, so our z-score is going to be equal to, let's get our calculator back, 5 divided by 2.3 equals 2.17. Okay, hopefully I haven't made any math errors here or interpretation errors. Let's see what I got here. More than 25, okay, that's what we asked. Okay, so we need to know what the value, what's the probability that we would have an outcome with a z-score greater than 2.17. We know that z-score is 2. We're already in the range where we would expect that right tail to be less than 2.5%, right? So we're going to get a result here less than 2.5%. So it's always good to kind of like put this into perspective, looking back at your empirical formula. So this is going to be a pretty small percentage. Let's actually look it up on our z-table. Okay, so 2.17, 2.1, 0, 1, 2, 3, 4, 5, 6, 7 would be 98.5%, 0.980. So, if I can't get back to my sketch there, fighting me. Okay, so here's my normal distribution. Our z-score to the left of that is 98.985, 98.5%. So that would be 1.5%, 0.015, or 1.5% chance that we would get from our sample 25 bikers out of the 50 that would have a mom tattoo. Okay, so we can use this normal approximation to help us determine what the likelihood of these different outcomes might be. Okay, so hopefully I haven't made any mistakes here. If I have made a math error or something like that, I'm sure you guys will catch it and let me know. But I hope this helps, and I hope you guys do great on the test. From what I can tell from the homework, most of you guys have been catching on to this material, so I have high hopes for you. Okay, so good luck on the test, and I miss you guys, and I'll be back in the city in about a week, and hopefully we can pick up where we took off from there. Okay, take care and good luck. Bye.